In the previous video, we developed a general expression for the Reynolds transport theorem for some stuff B, and then showed how that generalization was congruent with our previous analysis of conservation of mass, basically illustrating that we had already employed the Reynolds transport theorem for conservation of mass. Now I want to spend some time and apply that same theorem to the conservation of momentum. So as you might expect, we're going to start with the general form of the Reynolds transport theorem, and here it is on the board. And what we're going to do is now substitute, just like we did for the conservation of mass, we're going to substitute in our definition of B, lowercase b, like this, which is equal to stuff per mass. We're going to say it's equal to mass times the velocity vector, so that's our momentum, mass times velocity vector, if you recall from your physics, divided by the mass, which gives us simply the velocity vector. Similarly, we're going to have capital B, which is going to be just the momentum, so it's going to mv like that. Okay? So that gives us our definitions for our lowercase b and capital B, and we can then plug those directly into the Reynolds transport theorem. So we're going to get d over dt of mv is equal to d over dt integral over the control volume of v rho dv plus the integral over the control surface of v rho v dot dA. Okay, so that is Reynolds transport theorem with momentum plugged in. The next thing we want to do is take a look specifically at the left-hand side of this equation and see if we can't come up with a better expression for this term. So let's think a little bit about that. So the first thing we notice in this, the total derivative of the momentum, is that the mass is going to be constant. So we can pull that out. So we're going to have m d over dt of v, right? And then the next thing is that this term, d, the total derivative of the velocity, is the acceleration. So we can replace this whole term with the acceleration vector. So let's do that. So we're going to get equal, this is equal to the mass times the acceleration vector. And then if you recall from Newton's second law, where the sum of the forces is equal to the mass times the acceleration vector, then we can say that this is equal to the sum of the force vector, like that. Okay? So now we've taken this term and made it a sum of forces. All right? So now we can write out the sum of the force vector is equal to d over dt integral over the control volume of rho v dot dv plus the integral over the control surface of rho v dot dA. All right, and this gives us Reynolds transport theorem for momentum, and it is Munson equation 5.22 in your book for reference. Okay, we often don't leave this equation in this form. We separate it out into its components. So I just want to write that before we move on to the next thing real quick. So what we're going to do is just write out all the components of this force vector. So what we're going to end up with is the sum of the forces in the x direction is equal to d over dt integral over the control volume of rho u dv plus the integral over the control surface of rho u v dot dA. And what I want to point out here is that we've substituted our x component velocity u for our so-called b term of stuff. But we leave the velocity vector in the control surface calculation because that is dependent. We want to make sure we get the velocities normal to our differential area. Okay? We can do the same thing for the y direction. We get the sum of the forces in the y direction is equal to d over dt, integral over the control volume of rho v dt plus the integral over the control surface of rho v dot dA. And finally, for the z direction, we do the same thing. Summation of the forces in the z direction is equal to d over dt, integral over the control volume of rho w dv plus integral over the control surface of rho w v dot dA. Okay, I made a mistake up here that you saw me correct, and this should have been a dV and not a dt. Okay, so that is the components in our three orthogonal directions of the momentum, conservation of momentum for using the Reynolds transport theorem. Okay, so the next thing before we move on and end this video, I want to talk about these here. What are those forces going to be? What forces are really going to be important when we think about the conservation of momentum? And what it comes down to is there are really two primary types of forces that we need to be concerned with when we're doing these types of analyses. And the first one is body forces. And body forces, if you remember from physics, are forces that act on a body from a distance. And examples of these are weight due to gravity and electromagnetic forces. And in this course, the weight due to gravity is going to be the primary one. And in that breakout that we did of the different components, it's only really going to show up in our z component of our momentum equation. Okay? The second type of forces is surface forces. It's forces that act on the surface of our control volume. And the examples of those are pressure and shear stresses. So we've dealt with pressure somewhat already, and we know it's an extremely important in fluid mechanics, and specifically the differential pressure. We will introduce shear stresses a little bit later, but for now it's convenient to say that the flow is non-viscous and there are no shear stresses. But those are the two important ones that will come up when we start doing these analyses of conservation momentum. Okay, in the next few videos we'll do a couple examples of employing the Reynolds transport theorem to the conservation momentum to solve a fluid mechanics problem.